up here is just the same thing as this, but with active ones.
It comes back and starts looking. Like he like reaches the door and it's like.
Yeah, 2.4 is just inside here. Yeah. Just
This was kind of.
yeah, according to the yeah. Yeah, this gives me I use so I'm also writing out the
What have I done that exact same thing like 50 times?
yeah, that's what I thought too. In fact, my answer I used right up. So we're giving I0 letter is good.
How would I expect this? How large? You use Rust? I like it quite a bit.
It's just the same.
I didn't go to the restaurant and because a lot of I assume this is with the other contributors, well, the moderation.
And I also checked. I assume.
I mean, it's just it's popular. It's popular. All the stories. That makes it interesting. There's Amazon, Microsoft that like actually. I'm sure there was probably some crazy drama in C++ that happened 4 years ago.
Yeah, like C++, you're all like standardized.
That's a lot.
Rust doesn't even have a proper spec. So.
Oh yeah, I could use all my HKs just for the principle. Use all my HKs and then just
Once Rust has its back and all the real
Probably not, but you know.
what do you think next semester?
Is it okay if I just like
taking couple of us are taking boards that we get.
almost peak out of
For 12 is
databases. I'm taking.
yeah, it's the same thing with the 6th question, the last question.
I am currently told that, and I'm thinking about whether or not to use it.
That's the problem.
Well, no, it's no, I'm not like this semester, but like I'm gonna take it. But like my thing is like if it's just like a hard class and like it's fine, like who cares? Like,
Yeah, I know, but if it's a hard class, not by a professor.
it sucks, yeah, like. But cool, really learning.
Yeah.
That's
Because like of the two classes, there's one
we
that
also
I
have
don't want to
this-
take any
more
class.
So you can take it.
I'm taking it right now. I'm taking it right now.
So you had a, how many results? Okay.
No,
It's a lot worse.
I was really good.
Yeah, so basically I'm teaching 9 classes. So like, it's not. Yeah.
yeah. This is
It was really important. Those are classes where they tell you can't use like an I or like an index, you use like you can't use single character variable names. Yeah. Yeah.
yes.
But this is our class left.
Right, like this one where I
Oh yeah, it's 127. And I was using the tool correctly. That's how you yes, that makes sense. Yeah.
See what's happening there? It can't tell whether it's here or there, but the moment it realizes that part is there, this disappears. This is what you do if you have a map and you're trying to figure out where you are, and you only have the local information, and so you're trying to localize yourself on the map. That's what the robot is doing there. It's called filtering. So in the beginning, it thinks it's anywhere in this map. And as it's walking around, the data that it's getting essentially reduces the positional uncertainty. And the most interesting thing is right here, it turns out these two in some ways are symmetric. So it can't tell where it is until it comes in here and there is an obstacle there. And it, according to the map, it knows there is no such obstacle here. So it must be in this other row. Okay, so we will get started. So as I was saying, for those of you who are here, and I'll just repeat in case people came in late. I mean, it's actually only we are starting right now. So for those of you who just came right now, so this picture shows how robots localize themselves when they only have local measurements. So they don't have GPS and they're inside some environment and they're trying to figure out where they are. And they have the map of the environment. Have you guys gone through this kind of a scenario ever? Remember, there used to be these things called malls that people would go to before pandemic, before everybody is buying every damn thing on Amazon. So in the malls, mall look kind of like this. You have no clue where the heck you are, right? And then there will be every once in a while, there will be like a map. And the map will say you are here, right? So what it is trying to say is it is allowing you to localize yourself in the big map because you want to go to Neiman Marcus, you are in front of McDonald's. Neiman Marcus is in the 15th floor of the West Wing. You know, McDonald's is the basement of the South Wing, and you still need to figure out where you are so that you can go there. I think even now Google won't still work, although Google might actually be working, but you know, generally GPS denied environments, when you have GPS denied environments, you have to figure out where you are from local measurements. Okay, and this is basically what robots do for localization. And the thing that I wanted you to think about is what is the connection between this and the thing that we talked about before Thanksgiving, which is Bayesian learning. They're all connected, essentially. And filtering is an inference. Essentially, it's a probabilistic inference of a particular form. You know, it's trying to compute. So the filtering, originally, there is a distribution of the robot's position. You know, when it starts, when this picture starts, everything has red dots. That's sort of saying I'm uniformly present pretty much anywhere on this map. If it's more likely to know that typically I start on the West Wing, then there will be more dots on the West Wing, fewer dots on the East Wing. So that big set of red dots, that's kind of a distribution. And it has a sonar. You know, sonar basically, you know, hits off of the walls and tells it where, you know, what sort of reflections it's getting. Using that, it can sort of figure out, you know, some uncertain information about where it is. And in general, what is happening is that red things changing is there is a prior. After the data, you computed the posterior. You see what I'm saying? Every time it gets data, it's computing the posterior. And the posterior eventually can become quite peaked. That means it basically all the probability mass right now is only in two places. And a minute later, all the probability mass is just in that place. You see what I'm saying? You started with a completely uniform distribution and you got a peaked distribution. Peaked distribution means you know more about where you are. Another way of thinking about it is, that was that whole red stuff I was talking about. Another way of thinking about it, in the beginning, you have very high entropy. Basically, you have no idea where you are. By the way, it's very useful to think of entropy as connected to knowledge. High entropy, low knowledge. Low entropy, high knowledge. Which is exactly why a uniform distribution has high entropy. A peaked distribution, a distribution where all the probability mass is just in one part of the space, basically that means you have a better idea of where you are, right? And that has lower entropy. And so if you want to say, I don't want to assume anything as to where I am, start with high entropy distribution. That would be like a uniform distribution. And as I mentioned at some point of time earlier on, and I think Matt Zurenka was actually able to guess this, that uniform distribution makes sense for discrete scenarios, for continuous variables, -infinity to +infinity. if you are looking for an analytic distribution that has the highest entropy, that's what Gaussian distribution is. So which is why it's very reasonable if you don't know anything, saying it's a Gaussian is reasonable. Because anything else has more knowledge or lower entropy under some reasonable conditions. Okay, yes, go ahead.
High entropy is like, in the case of this robot, they don't know where they are.
Exactly, high entropy means high uncertainty.
So then, if two rooms were identical, like say the top two rooms, like the same layout, same objects and such, and the robot starts like going into one of those rooms, and so that would mean that it would have the red marks in both rooms.
Yeah, so basically the red marks tell it, think of those red marks as the probabilities.
Okay.
Each of those places there is non-zero probability.
So
In fact, in general, there may well be everything is non-zero except the white parts are like very, very, very close to zero.
So then if you have two identical rooms and you have many probabilities in those two spaces, is that a state of high entropy?
No, I mean, it's compared to what? Compared to the beginning where you could be anywhere. So imagine the following thing. This is the thing that people don't understand. They assume random means that there is deterministic and there's random. Okay. In fact, this is why these nonsensical things come. For example, people with vaccines also can infect people. So what's the point in taking vaccines? That's because you are innumerate. You are misunderstanding the probability of infection is much lower if you're vaccinated. It's not a question of yes or no, it's a question of what is the probability. So random doesn't necessarily, random only means it's not deterministic. But the degrees of determinism, if you think about different, so if I say, I am somewhere in the university right now versus I'm somewhere in brickyard right now, both are uncertain. But which would you rather have? Brickyard is much better. I mean, especially if you're trying to bomb the place so that I'll be gone, you have fewer bombs to use. Right? Do you understand what I'm saying? So in general, the entropy essentially says there's a much higher uncertainty. So in the very beginning, there's very high uncertainty. And as you're going forward, the uncertainty is sort of reducing. It can also increase, by the way, in a static environment like this, where only the robot is moving, uncertainty can't increase. But if it's a dynamic environment and things are being, basically there are other agents which are trying to change the layout or putting more obstacles, etc., uncertainty can increase again. But the point is, remember, you started with a prior on your position. You took the data of your current local positioning, and then you computed a posterior on the position. My question is, how is this connected to Bayesian learning? You start in Bayesian learning with, Bayesian learning with a prior over the hypothesis. Remember this? We were talking about this. I'm sorry, I actually meant to make you watch some more Bayesian learning stuff, but I forgot. And by the time I remembered, I thought, Thanksgiving weekend, you should probably enjoy it. So you have to remember what we were talking about last time. So we started with the prior. In this case, the prior is actually not uniform. That means I had some knowledge about how the bags were. What were the fraction of the bags, were of H1 type, H2 type, etc. And then as the data kept coming, which is lime, right? The posterior, this is the prior. And then after the first lime, after the first line, the posterior changes. In particular, notice that after the first line, the red distribution became zero probability. Why is that? Because the H1 is 100% cherry candies hypothesis. The hypothesis that there are 100% cherry candies becomes zero probable the moment you saw one line, right? So that's what you're doing. As you're seeing lines, essentially the posterior on the hypothesis is changing. By the time you've seen all these lines, your posterior is actually like this, where you really see that the probability of H5, which is all lime candies, is much higher. Actually, it's also written here. Probability of H5 is much higher. The other ones are still kind of there, because except for the 100% lime, everything else is still probabilistically possible. Low probability, but it's still possible. You understand what I'm saying? So that's what you're doing here. So you started with the prior, you are getting data, you're computing the posterior. Based on the posterior, you know what is the current posterior and the hypothesis, and based on that, you are then predicting for the test case that will come, what is the probability that it would be cherry. It would be, I think in this particular case, probability that's a lime. And 1 minus that would be the probability that will be cherry. Do you see what I'm saying? Do you now see the connection between what we are doing here and what the robot was doing in trying to localize itself? And what robot is doing, do you want to call it learning its position or reasoning about its position? It's more, the point is there is really not much of a difference between learning and reasoning when you think in terms of these distributional differences. If you have a Bayesian view, there's no difference between learning and reasoning. Which is why, I think I mentioned this maybe just before we left. That Bayesian learning is an oxymoron, because many people tend to think learning means picking a winning hypothesis. Most of you think so. Tell me exactly what the class is. Right? Get rid of that. The most general case of learning is reasoning about how the hypothesis prior becomes posterior as you have seen the data. And once you have the posterior of the hypothesis, you can always use a weighted computation to figure out what the new data points class is. So if it is H1 says the class would be, let's say C1, but H1 is only 10% probable. H2 says the class is C2, it is 90% probable. So the class is 0.1 probability C1 and 0.9 probability C2. You understand what I'm saying? And at that point, if you keep the distribution and if you decide to collapse the distribution and take the winner, that's a different story. But the idea really is learning and reasoning are very closely connected in the Bayesian view of the world. And in fact, what the robot was doing is called filtering. And when we built our the hypothesis, we called it learning. So learning is filtering. So which is basically what we are saying. Learning is not just optimization. Learning is in general filtering or inference over possible hypotheses. And this is where I'm getting to. This is where I basically had this quote. Do you guys remember who said this? Come on, guys. Yes. Sherlock Holmes said this. So Sherlock Holmes basically said, when you have eliminated all that which is impossible, then whatever remains, however improbable, must be the truth. That's filtering. Sherlock Holmes was doing Bayesian learning. He was doing filtering of the possibilities so that what are the remaining possibilities as to who did the murder in his case. Okay, this turns out to be an extremely important insight to have, even though in your life you'll keep on thinking learning involves essentially, starting some sort of a gradient descent and finding a single winning hypothesis. You have to realize that you do that because doing this is costly. In fact, I'll tell you in a minute that this is the heaven, this is the way to do learning. It turns out to be too costly, even now. So people approximate it. And there are different ways of approximation. And some of the greatest ideas we have seen, including dropout, are essentially an approximation to Bayesian learning. And really bad approximations are what are called maximum likelihood estimation, which is what you guys do. Maximum likelihood estimation will be like fitting a curve, just fitting a curve to the points, so to minimize the error. MAP is a slightly better approximation, maximum a posteriori, and that turns out to be fitting a curve to the data to minimize the error plus some complexity term about the curve. You understand what I'm saying? Because if you don't care about the complexity of the curve, you know that you can do a very crinkly curve that goes through every damn point. That will be zero error. And in fact, much of the stuff that we discussed about learning, such as there is overfitting, you need to do regularization, all of that becomes much easier to understand when you realize that what you should be doing is this, filtering. Since it's too costly to do filtering, you approximate. When you do approximation, you will wind up doing overfitting. And then you need to add regularization term. Okay. Yes, you had a question.
I would say, so like on the candy example, like the ones that are the first hypothesis, they don't actually go to zero, right?
Which one? Yeah, they'll never go to zero. In fact, the ones that are not, these things are never really zero. They're becoming closer and closer and closer and closer to zero. Because every other bag other than H1 has some % of cherries. Do you understand what I'm saying? So there is a probability that the first, some % of limes rather, sorry, some % of cherries and some % of limes. So they can explain, so a 75% cherry, 25% lime bag still can explain all limes that you have seen up until now, because all you have seen till now is how many data points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 25% cherries, 75% cherries, 25% limes. And if we keep randomly picking, it is still possible to get 10 limes consecutively. In fact, here's a question. What is the total number of limes you can get with replacement in a 1% cherry and 99% lime? Sorry, 99% cherry, 1% lime. So it's mostly cherries, just 1% lime. From this bag, if you are picking, what is the probability that you can get? When will the probability that you can get K limes in sequence will become zero? Do you understand what I just said? So 10 limes maybe is low probability, it will still be there. 100 limes, will it become zero? Million limes? No, it will never become zero. It just become really, 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 really small. By the way, here is a very interesting point about that. In probabilities, the thing that you really need to be careful about is not whether your prior is correct or not. Because even if the prior is incorrect, the data will override the prior. You understand what I'm saying? Suppose you didn't quite know what percentage of the bags were there initially. These guys told you, but suppose you got wrong information. The data will eventually be so much that it will correct any errors in the prior. Right? In fact, this is a way of understanding why maximum likelihood ideas work, because maximum likelihood ideas we'll see in a minute, they work because eventually the prior doesn't matter. There's enough data that posterior is sort of quite insensitive to the prior. for large data problems. This will be true only under one important condition. One important condition, which is the prior is not zero for any possibility. Prior is not zero for any possibility. Understand this. This is why we have these things called positive distributions. A positive distribution essentially makes sure that at every point the distribution is non-zero. You know that it cannot be negative anyway. Positive means it's not even zero, it's non-zero. It's very important because eventually there's all sorts of interesting philosophical points that can be made about this. If you allow for the possibility for any hypothesis to be true, if only with extremely low probability, then during your lifetime, if you see enough examples, you will reach the optimal decision making, even though you had bad prior to begin. You understand what I'm saying? Imagine you had a bad prior saying Indian teachers are not going to be good. And you said for that probability is zero, Indian teachers being good to be probability zero. Then even if you see infinite number of Indian teachers who are good, you will never change your mind. If on the other hand, you just said, I haven't seen enough Indian teachers being good, so I'll just give it a 10 power minus 7 probability to begin with, then there is a hope. Positive distributions allow you to change your mind, probabilistically speaking. Zero is forever. In probability, zero is forever. By the way, this will come back when you do naive Bayes classifier, where we'll find that there can be zeros sometimes when you're doing this thing, and you never want zeros. So you add a little to the denominator, you'll add a little to the numerator, just to make sure that it'll become positive. And you'll come up with a fancy name for it, saying Laplacian correction. What you're really saying is, I don't want ever to completely disallow anything. You understand what I'm saying? It's a very philosophically amazing point. Zero is the only thing that's forever. So as long as you're not zero, data can override your prejudices. And by the way, the priors, remember the whole frequentist versus, I'll have to get this. Yeah, so first of all, I should say that this stuff is not obvious. So the last time around when I was teaching this 2 years back, I threw it on the web, on the Twitter. And Tom Dietrich and Jan LeCun and all these people were arguing with me. Okay, turns out eventually they had to admit that this stuff makes sense. Most people who start doing machine learning don't understand that Bayesian learning is really what you wanted to do, and everything else is best seen as an approximation. You understand what I'm saying? So you're ahead of the game if you understand that. Okay. So was there a question that I missed? Yes.
So in the case of the candies, the prior is basically the exact number of bags that you have.
Prior is the percentage, basically the probabilities. The percentages are less important. Prior is the probability of finding bag of type H1, probability of finding bag of type H2, etc.
So when you're learning so after each posterior is computed, you update the prior.
No, basically it becomes posterior. You don't update, when you update the prior, it becomes posterior. Prior is before seeing any data. You understand what I'm saying?
And based on anything?
What?
Prior isn't based on anything?
Exactly. This is the worry. She is channeling the worry that frequentists have. Let me see if I can get there. That is basically before you see data. Remember, I showed you this? The real big difference is that, first of all, Bayesians say that probabilities are subjective. Frequentists say no, they are actually asymptotic frequencies. Then Bayesians say hypothesis is actually a random variable, so I can put a prior on it. Frequentists say no such thing. And furthermore, they say, where will you get your prior? Exactly like, I think what's your name, Emilia, right? So what Emilia is saying, it looks like you're making up your mind before even seeing the data. You can say that's a bad thing. You can also say that's a great thing. You did not fall off the turnip truck before you saw the data. You have lived a successful life. You have knowledge about the world. When you opened the door, your prior said there will only be higher probability that there are people here, lower probability that there are going to be dogs here. If you don't want to make any judgment, I don't know, I would just wait to open the door and then see who are there. What's the advantage of not using the prior knowledge that you have? Your entire life is given you experience. Statistics people basically try to make this the frequentist statistics people try to make this nonsensical assumption that we should not know anything other than the data. But they don't really mean it, honestly, because the data is coming from various causal mechanisms. And you have some idea about how things are connected. And there's no advantage in not using that. And you might say that is prejudice. So again, it all depends on this guy has empty head can be seen as a positive or a negative thing. This guy has a bias can be seen as a positive or negative, a prejudice. Prejudice essentially means before seeing the evidence, you already have an idea. My point in this class is if you are ever a juror, I'm fine with you having prejudice distributions. You might well think that, Indians who look like Rao are likely to be criminals. I'm not going to stop you from it. I can't stop you. Even if I try to stop you, you might keep that. You are smart enough to not say that aloud, and so you will get onto the jury. My biggest worry is you will give 1.0 probability for that and give 0.0 probability for the defendant not being guilty. In which case, how much evidence we present, posterior is not going to change for you. If on the other hand, you just said, I'm more likely to think this guy is looking somewhat shady. Maybe he's like he or she is like a guilty person. But you kept your open mind. Having open mind doesn't mean I just fell off a turnip truck. Okay. Having open mind means I am willing to change my prior in light of the data. This is a much better way of understanding what we mean by. So it indeed is what Emilia is saying is the big religious wars between frequentist and Bayesian statistics people. Frequentists say, how the heck can you get prior? First of all, what do you mean hypothesis is a random variable? He said, no, it's a random variable anyway. In fact, you basically say, Bayesians say hypothesis causes data. Hypothesis variable causes the data. Because of which, by the way, if hypothesis is given, D1 is independent of D2. Do you understand what I'm just saying? Right now, this Bayes network is a meta Bayes network. It has the hypothesis as part of the network, along with the data in it. And the same ideas we understood about conditional independences make sense. Given the hypothesis, the data are independent of each other. This is what we actually mean by IID. Okay. Now, frequentists don't like this at all. So they say we can't like this. And then basically, these guys say, well, since anyway we are saying it's a hypothesis, we'll put a prior on it. Then the frequentists come back and say, oh, yeah, but where are you getting the prior? The answer is because I haven't fallen off the turnip truck. So I have some idea. If I'm wrong, I'm going to change my mind. It'll take more data, but I'll change my mind. If I'm right, I will get to the right conclusion faster because I'll take less data to get to the conclusion faster. As long as I have a positive prior, non-zero prior. Okay, now then they'll say, well, if you don't have any kind of prior knowledge about this domain, That means for as far as this domain is concerned, you actually did fall off the turnip truck. By the way, I don't know if people know this thing called falling off a turnip truck. Essentially means I don't know anything. So this is like an Indian teaching natives what their proverbs are, okay, and what their idioms are. Now, falling off a turnip truck basically means I have an empty head. Don't know anything. Okay. I assumed you know this, that's why I was using it. So anyway, so if you did have completely empty head about this domain, then how would you get the prior? Frequentists will say, yeah, look, we caught you. I say, no big deal. I will just pick the prior to have the highest entropy. Highest entropy means the lowest amount of knowledge possible. For discrete scenario, that means all hypotheses are created equal. For continuous, I'll take some kind of a normal distribution. You guys see what where I'm going through? And in general, this kind of connects to many ideas like prior distribution is equal to prior knowledge. And prior distribution as well as prior knowledge constrain learning, so you get to the conclusion faster. Ultimately, if you have tremendous amount of data, then priors don't matter, because as long as they're non-zero priors, they will be overridden by the data. The big problem is when you have only a couple of data points. Right now, the biggest problem in machine learning is not for the large data. Large data, we know how to deal with it because priors don't really matter for the large data as much. But they matter for the small data. That means you have few training examples. If you have only few training examples, Bayesian learning works completely fine. Because it's the same theory, whether it is small or large number of examples. Everything else will start having all this overfitting and not enough samples and all that fun stuff. Yeah.
So, if you were to learn using the frequentist method, would that be similar to operating simply on tacit knowledge?
No. This basically Bayesian learning, when it is approximated to MLE, where basically you are saying, I'm essentially just going to look for the winning hypothesis, not the posterior, but just the hypothesis that's most likely. I want to just learn that. That will become maximum likelihood approximation of Bayesian learning. That is basically the same as what frequentists do, but they call it something else. They have a different motivation for coming to that point. Okay, that's what that is. Okay. Any other questions? Yes.
Bayesian learning is just about having like domain knowledge.
Bayesian learning allows you to have domain knowledge. It allows you to maintain disjunction in your head about different possibilities. Just because you have the option doesn't mean it becomes imperative. Right? Whereas this guy doesn't at all, because this guy just thinks there is a single hypothesis and you're fighting confidence on that. Yes.
So like in the example of limes and cherries.
I'm sorry, what?
In the example of the limes and cherries in the bag, like after you see 10 limes in a row, and then you try another bag and it's 10 limes again, you start changing your prior, like.
No, remember that you only have one bag in front of you and you're trying to pick from this bag. You just don't know. What you really want to do in the lime example is you want to predict what's going to be the next thing that I'm picking without having to look at it. That is P. Basically, the learning problem is what is the flavor of X given all the candies that you have seen until now. That is written as essentially data, which is the candies, and the hypothesis. That means given X, what is the power of X given D as well as H? And since the H causes D, according to your model, that means hypothesis caused the data, given D and H is the same as given H. I'll show that in a minute. Okay. So what you're trying to do in that candy example is really figuring out what's the next candy going to be. You're going through this intermediate step first, saying I first have this hypothesis about how candy bags are made. And based on the hypothesis, what is the likelihood that the next candy will be lime or cherry? Okay. Actually, let me show that to you since I said this. I mentioned this last time, but I was probably too fast. I'll show that to you again. Where did that go? A second. Okay. I cut that one off by mistake. Yeah, this one. Yeah, this one. So this is the slide that was there between the two pictures that I didn't go through step by step last time. Okay. So what we are saying is we are assuming that hypothesis causes the data. And what we are trying to do is we are assuming that there's a prior on the hypothesis. And when you see the data, then you are computing the posterior on the hypothesis, which is PHI given D, which can be written in terms of D given HI and PHI using Bayes rule. Right? H given D can be written in terms of D given H. Now, by the way, in this case, in this hypothesis and data case, what if you think in terms of the last time we thought of Bayes rule particularly significantly was in the context of diseases and symptoms. So what are the diseases here? What are the symptoms here?
Diseases, H and the symptoms are H.
Hypotheses are the diseases. Data are the symptoms. You see symptoms, you want to guess diseases. Medical textbooks are written given the disease, what is the possibility of the symptom? So similarly, data likelihood, probability of D given HI is much easier to compute, right? Because if I assume that this is a 25% cherry, 75% lime bag, and the data is a cherry, then D given HI is 0.25. Right? You understand what I'm saying? So basically, this stuff that you had about the stuff that you had about the various bags, that was your medical textbook for the bags. Which hypotheses have what level of symptoms, cherry versus lime symptoms. And when you see that it is a cherry, and you know that the bag is 25% cherry, 74% lime, then the probability D given HI is 0.25. And you also know PHI, which is the prior probability just before you saw this data. So you can compute the posterior, PH given DI. The normal thing, of course, is here you should say D given HI times HI by PD. Probability of data itself. That's like probability of symptoms itself. And we know that normalization trick takes care of that. If you're computing the entire distribution, you can assume that it's alpha times that, and that alpha can be computed by adding all of them and equating it to 0, equating it to 1. You guys remember this stuff? For those of you who remember, it's all nice enlightenment. For those who don't, I mean, unfortunately. Okay. So you can do this. So you computed the posterior. So essentially, in that picture, how the posterior is computed was like this. Those numbers are not made out of thin air. You can compute these numbers because you know PHI, you know D given HI. So you can compute those numbers. And then the last one is predictions. I have a data X, and I want to know whether it's cherry or lime. The simplest learning problem really is having seen so much data, of cherries and limes till now, what is the probability that the next one is either a cherry or a lime? This is really what you're trying to solve, X given D. And what hypothesis says is, let's assume there's an intermediate hidden variable. When did we randomly introduce a hidden variable? Remember when Bayes networks, when we wanted to reduce the number of numbers you need to give, we started introducing hidden variables. That's exactly what we do here. The hypothesis makes sure that data are no longer dependent on each other. Given the hypothesis, data are independent of each other. So you introduce this hypothesis space. And so then you have a Bayes network like this. And so you're essentially saying Px given D is nothing but Px given D and Hi times Hi given D. You sum it over all the hypotheses I. In this case, this is a discrete problem, so you sum. If you're doing it continuous, it will become an integral. That's what Bayesian inference is. And they actually call it Bayesian inference. They don't need to call it learning because it's just basically the same inference. Okay. So did that answer that gentleman's question? What is happening in terms of the candy boxes? So really what you're trying to do at any given point of time, the other beautiful thing about this is when you start, you haven't seen any data. So that's your prior is PHI. After seeing one data point, now you have a posterior. The second data point is coming. For the second data point, the prior is the first data point's posterior. You don't just go back to the beginning, right? You have already seen the first data point. So now you have a new posterior, which becomes the prior for the next data point. You guys get that? That's exactly what filtering is. And so at any given point of time, I say this much is the data. Can you tell me what would be the next guy's expected label? You would use this formula at that point of time, using Hi given D as the current posterior after seeing those many data points. You don't even have to see all the 10 that I gave. After the first one, you can do this. After the second one, you can do this. Which is why that picture basically, I'm sorry, where am I with the picture? This picture, you notice what is happening. At any given point, I can actually guess using Bayesian hypothesis space what's the probability of the next candy being a lime. And this one is done by essentially this weighted summation. So it is incremental. It is any data. It doesn't need humongous amount of data. One of the nice things is if you have a large amount of knowledge, with one piece of data, you may be able to learn. In fact, the difference between the learners in the class here is not your gradient descent algorithms that you're using in your brain. It is your prior knowledge. Or, at any given point of time, today's class, before you came into this class, you had a prior distribution of concepts. And how much I have to repeat what I'm saying today depends on how good your prior distribution was. And it is true that you could have had wrong prior distribution. You misunderstood something about A-star search. That means I have to give you even more data points than the guy who has an empty head. But if you actually understood something, I have to give you much fewer data points for you to understand the next concept. Knowledge is what makes learning easy. In fact, there is a statement I forget, which says that we only learn those things that we are almost already know. Which is exactly why you are taught intro to AI now. You are taught, quantum mechanics in probably your third year or something of your bachelor's. Instead of, why not repeat quantum mechanics in the grade school for Timmy and Mary until they get sick and tired of you. Just keep repeating multiple examples of quantum mechanics. They do have a brain. They should be able to learn. They might die out of boredom, hopefully, and you might be put in jail. But really what you're doing is you are scaffolding. You are essentially getting them to the next level and then teaching one more thing. By the way, there is a name for this in the current learning literature. It's called a curriculum development. Where did the word curriculum come from? What you guys do. Okay. So this is all great. But Bayesian learning is too costly. That's the sad part. Then what you want to do, you basically, if we know that if we have a computational power, the full Bayesian is the way to go. In particular, things like overfitting, things like too little data, none of those are problems. With respect to the knowledge you started with, Bayesian is always going to be the optimal learning, but it's going to be costly. So you try to do various approximations to make it work. And some of those approximations you have already seen without knowing all this stuff, although I kept repeating Bayesian learning to the point that it probably is anticlimactic, at least to some of you, when we actually got to it. Okay. But dropout is Bayesian learning. It's an approximation of Bayesian learning. In fact, there is this other idea called random forest, which I did not. So this is a dropout. I showed this to you and I pointed out multiple times. It's kind of an approximation of Bayesian learning. There's this other idea called random forest, which I didn't actually talk. By the way, this is another example of a good learning technique that you should read up. Normally, if I had time, I would have taught you decision trees. Decision tree will just get one great decision tree for the data. Random forest says pick a random subset of features and only with respect to those features compute a decision tree. So you'll get a forest of trees. And then all these forest of trees will then try to guess the new data points label and you take a weighted average. What does it look like? Look exactly like Bayesian learning without probabilities. And random forests are one of the great ideas, just like dropout. Random forest is one of the go-to ideas that data scientists use for categorical attributes in particular. The difference again is you are avoiding making up your mind about a winning decision tree. You are computing a bunch of decision trees, each acting as if they're only a random subset of the features. Okay, and then essentially making these multiple experts vote. It's a kind of an ensemble learning, and it actually works. And when you see this, you say, yeah, that's where it came from, Bayesian learning, which we are supposed to do, which we aren't doing. We found a way of doing it, right? There are other ways you can do it. In fact, a very sophisticated way. This, if you actually look at those tweets, there are some tweets on that. Jan basically talking about variational free energy. So I should explain to you that what variational Bayes does, unfortunately, I won't have time here, and it's also a little out of scope, is it is true that the entire posterior is hard to manipulate. It was easy enough for the 5-class problem where it's a 5-class discrete probability distribution. If you have an infinite set of hypotheses and you have to start with a prior and you have to compute a posterior, one of the big issues when you have continuous case scenarios, pay attention here. Imagine you have a continuous scenario. The prior has to be given an analytical distribution, something like Gaussian, right? Then you compute the posterior using Bayes rule. What if that's no longer in normal distribution form? For the continuous distribution people, the biggest nightmare is that they start with one type of distribution which has like 3 or 4 parameters, which will then explain the entire probabilities, infinite number of probability densities. And then after the posterior computation, you get a different form of distribution. That requires a different formula. In the end, actually, there may not even be any formula. You see where I'm going. So one of the strangest things Bayesian learning people do, when the implemented Bayesian learning systems do, there are a few of those, is they will always try to pick as prior a distribution that is what is called conjugate to the transfer, which is d given h. Because posterior is p d given h times p of h, right? D given h times p of h should still be of the same form as p of h. If that is the case, then the prior is considered to be conjugate to the data likelihood. You understand what I'm saying? Is that a reasonable assumption? No, it makes math easy. If it is conjugate, then you will still essentially have the distribution be of the same form. So if it was a Gaussian with a mean and variance, it will be a new Gaussian with another mean and variance. You still just have to remember two numbers. You guys understand what I just said? So in particular for filtering, how many of you heard of Kalman filtering? Nobody heard of Kalman filtering? It's like one of the most, in fact, Second World War was won or lost based on Kalman filtering. Because this is target tracking. It's like that filtering that I showed you earlier. Kalman filtering essentially does Bayesian filtering. So you can think of filtering as learning, as I said. What it realizes is normal distribution is conjugate to normal distribution. So if you have a prior as normal, likelihood as normal, posterior will still be normal. So you jump up and down and you write nice bunch of formulas saying the only things that change is the mean and the variance. You don't understand how great this is. Because if you start with some nice, distribution which can be described by mu and sigma, which is the mean and variance, and then after multiplying by PD given h, I get something like this. What do I do with this? You see what I'm saying? I don't have a formula for this. So then basically, Kalman filtering, in essence, what you'll do is you'll make sure that this is normal. Even if it's not normal, you'll make it normal. So that when you multiply normal by normal, you get a normal. This is a second order version of searching for the lost keys under the light. You're doing this not because this is what the problem needs. You're doing this because this makes the math work out easy. Do you understand what I'm saying? It should just blow your mind. Sometimes you do things just because the math works out easy and you hope for the best. Okay? It turns out that there is actually a better way of doing that kind of a filtering without making the Kalman assumption. Okay? Which essentially is what's called particle filters. And the textbook has, and I think one of the sections at least actually covers different sections of 471, 571 are covering different topics. I think at least one of those guys covered particle filters. The picture that I showed you earlier is actually a particle filters at work, because it is using the distribution represented by samples rather than by analytic expression. It is not analytic, it approximates, but it approximates any random thing. Just one second. This class became mostly to blow your minds because last class, hopefully we'll get back to something simpler. But notice that the particle filters can be used to do this. There's some other thing you can do, which is if you have some random distribution, I think I mentioned this once. If you have some random distribution, the textbook distributions don't have a formula for this. You can't fit a normal because it's not normal. It's not a skew distribution. What can you do? This is a function. You represent this as a neural network. Because neural networks can represent any functions. You see what I'm saying? Any arbitrary function can be represented by neural networks. So in some sense, actually, one of the interesting ways of doing this sort of reasoning, this sort of Bayesian filtering, for example, is to represent arbitrary distributions as neural networks. This, if you are crazy enough in this class, should remind you of what we did for reinforcement learning when we started saying the value function is a neural network. And we started changing the weights of the value function instead of changing the states. States values directly, you started changing the weights of the neural network. That sort of a thing is possible. A third idea, which is actually variational Bayes, is in fact, I think the neural network approximation is already variational Bayes. But one of the things before the advent of, in general, one of the things that people did up until in the beginning is try to look for things with analytical expressions. If you don't have analytical expressions, somehow fit it to some analytical expression. The new AI, generally new data science, is instead of fitting it to something that we have just happened to have made up before. Actually, I have a tweet on this. I'll remind you. I mean, some of you may have seen this. Things like student T distribution or some, geometry distribution. You can just, they're just functions. You can learn the distribution in a compact form as a neural network, where the weights of the neural network would be such that it will, which basically approximate it to the function. So the named, remember I said named filters went out of the window in image processing. Named distributions are about to go out of the window. Gauss will feel sad, but who cares? Right, see what I'm saying? The old ones was everybody would come up with a nice, cleanly defined analytical distribution. Why waste time on that? Let a function approximator figure out. And in fact, particle filtering is, so you have simple analytical, complex analytical, which is a neural network, particle filter, which just approximates the entire distribution by samples. You understand what I'm saying? And the thing is that approximating functions by samples is not anywhere near as efficient as approximating them by some primitive functions like neural networks do. So when possible, you might want to combine both. And in comes the only thing that has my name, except not me, unfortunately. You can look up in the textbook something called raw Blackwellized filters. Raw Blackwellized filters essentially combine the best of Kalman filters and particle filters. They still don't combine neural networks and particle filters. Okay. Now, having said all of that, in essence, what variational Bayes is that it's trying to represent the posterior using some family of distributions and trying to figure out, I'll say it will be the best line, and I'll say that the posterior can be represented as, let's say, some kind of a parabola distribution, and I find the best parabola. That's variational inference. It's still better than picking a winner. It's just approximating the distribution, but not exactly. Whereas picking a winner means approximating the entire distribution by just taking one point in it. Okay. It's way more than I really would expect you to remember, but I think the fact that you heard it might make you recall when you actually look at these topics again at some point of time. Okay. The other things is the simpler ones that we want to do, which is maximum likelihood and maximum a posteriori, which we will do here. In fact, we'll only do the maximum likelihood here. Okay. So how do we do that? Get out of this. Okay, wait. I think I'm skipping over a slide. Sorry, the order was all messed up because, yeah, this one. So notice this is the way you compute the posterior distribution. You could directly approximate the posterior distribution either by particle filters or by neural networks or by standard variational Bayes, where it tries to fit some particular form of distribution, the closest member of that family of distributions to the posterior. Now, whenever you're trying to fit a best member, that will again be an optimization problem. So variational Bayes has an optimization aspect to it because you're finding the best approximation to the entire distribution. Okay. Now, if you give up on all of that, what I would say is I can take the distribution and say, I really don't want to keep around multiple hypotheses. I want to pick the winning hypothesis. So if I am trying to equate an entire distribution by just a single point, what should I do? I should pick the hypothesis which will have the highest probability in the posterior. So I'm computing, this is basically for each of the hypotheses hi, it gives posterior hi given d. And what I want to do is pick the hi which has the maximum that value. That means pick the one that maximizes this. Pick the ith hypothesis that maximizes that. You can also say that maximizing this multiplication is the same as maximizing this logarithm. Because again, logarithms basically are monotonic. So wherever they become maximum, the other thing also becomes maximum. You only need to know the winning guy, not the number for the probability. Who is the winning guy? You do this, that means you're looking in a space of hypothesis. You're looking for the hypothesis that gives the maximum value to log PD given hi plus log of P given PH. If you do this, this is called map approximation. And if you go from here and say, I don't even want to do this, I just want to maximize PD given hi. I won't want to consider P given PHI at all, which would be like just maximizing in this sum, only maximizing this part and ignoring the second part. That would be maximum likelihood estimation. Now going backward, this corresponds to just minimizing the error from the training examples. This corresponds to minimizing the error plus a regularization term. What is the regularization term here? P of hi, which is somehow the probability, prior probability of this hypothesis is being taken into consideration. Prior probability of this hypothesis is being taken into consideration. That is the regularization term. And in fact, every regularization that you ever used, such as in minimize the size of the weights in the network, can be given a probabilistic interpretation. When you, for example, say minimize the complexity of the function, you are in effect saying more complex functions have lower probability density than lesser complex functions. And there is a general idea called minimum description length principle, which basically tries to capture that. that a complex function requires more bits to explain what that, to specify the function, more bits of information. Line requires much fewer parameters. So if you penalize complexity, in essence, you are saying the prior probability for complex hypothesis is lower. I don't know if this should make you feel happy, because previously we were just adding these regularization terms. There was no reason for it. Now we know why we are doing this, because this is essentially saying, even though this guy's runny nose seems to be cleanly explained by Ebola, Ebola itself has extremely low probability. So I'm not going to give this guy Ebola as the best diagnosis. Understand what I'm saying? That's a prior. Okay. So before we go off in the next few minutes, I'll skip over it and say, actually, I'll just show. Okay, sorry. And I'll continue this next class, but I'm just going to do ML, or maximum likelihood parameter learning for Bayes networks. And it turns out with all this, in fact, if you take a YouTube machine learning course, you will get to this first. And by mistake, you took my course. So you had to wait the entire class to get to this, because this is just detail. You need to know where the ideas come from also, to some extent. Because the rest, once this class is over, you'll just go to watch the YouTube videos. Okay, I need to know naive Bayes classifier. Naive Bayes classifier.flv will be there on the YouTube. That will tell you something. But you want to know how that is connected to everything else. That's what you hopefully will get it here. So what do I do in this case? Imagine here I have a bag from a new manufacturer. It has a fraction theta of cherry candies. Any theta is possible. That means the probability of cherry candies is theta. And this probability can be anywhere between 0 and 1, inclusive. It's a true real number, which basically means it does correspond to a Bayes network like this. It's a Bayes network with just a single node. The single node is the bag type. And the bag type basically is specified by the flavor, the fraction of the flavor. If there's only two flavors, so if you give one fraction, one flavor's probability, one minus that is the other flavor's probability. So you have a Bayes network saying probability F being cherry is theta. Why theta? I would have said P, but I remember I told you, you must use Greek letters. Why the heck are we saying Omicron? It's the same thing. Greek somehow makes us feel more sophisticated, except for Greeks who get confused because they have no idea what's going on, because their normal letters and all these sophisticated letters are the same. But anyway, so imagine it's theta, right? My question is, I need to compute this theta. How would I do it if I'm doing the maximum likelihood? I will first compute, given the data, I will compute the likelihood of the entire data in terms of theta. That will be an expression. In particular, imagine I saw n candies where there are L of them are limes and C of them are cherries. So L plus C equal to n. This is the training data. What is the probability of this data? Well, the first one, let's say, is a cherry. The probability of cherry is theta. The next one, let's say, is lime. The probability of that is 1 minus theta. Since these two are independent, given the hypothesis, you can multiply them, theta times 1 minus theta. If there are C cherries, L limes, then the total multiplication will be theta power L times 1 minus theta, theta power C times 1 minus theta power L, right? Theta power C times 1 minus theta power L. You guys get this? This is not rocket science. I just need to maximize this expression. What is the variable? Theta. I need to maximize this expression with respect to the variable theta, because that's how I get the maximum likelihood. right? Now, since you came here after already playing around with PyTorch and TensorFlow, you say, screw this, I'll just give this as my loss function and say, maximize this. Instead of minimizing the loss function, you need to maximize. So you just need to, you can still use the gradient descent, except you have to do gradient ascent because you compute a maximum. Loss is minimized, likelihood is maximized. In fact, you can just do that. But once again, remember, people were very interested in getting simple analytical formulas. If you look at the progress of science, we tried to look for analytical formulas, even when they are not actually right, because that's the stuff that can be written on a paper. Okay, so I'm going to basically take this expression, theta power c 1 minus theta power L, and maximize it with respect to theta. How do I maximize it? If I were to do it myself, I basically, this all looks like anticlimactic because we already know that you can just give it to somebody called gradient ascent and they'll do it. But if I'm doing it by myself from first principles, I'll take the derivative of the likelihood with respect to theta, equate the derivative to 0. That would be the place where either maximum or minimum or a stationary point will occur. And then if you take the double derivative test, you can also see whether it's a maximum or not. Do you understand what I'm saying? If you were doing this, you will never do neural networks of more than one level. This is the way we did neural networks for perceptron, remember. And then we did this computational graph and automated the heck out of the whole calculation. But here we are again coming back to doing it by hand because it turns out the answer just is so revelatory. So what do I do here? I want to maximize this. One of the points I say is I can maximize this by maximizing the log. So typically you take log likelihood. And like I said, log likelihoods are great because probabilities in the best cases will always be multiplications of exponentiations. Theta power c times 1 minus theta power L. You take the log, it becomes so nice. It's c times log theta plus L times 1 log and 1 minus theta. That is this expression. Okay. At this point, you do differentiation. Do you remember the $1 million thing that log x derivative is? What is the derivative of log x? 1 over x. Please remember that. In fact, you would say, why do I need to remember? It's like, just like kids have forgotten arithmetic because they have calculators, bigger kids have forgotten differentiation because they have PyTorch. Why do you need to differentiate? But anyway, so it's 1 over x, right? So if I differentiate this, I'll get c by theta times L by 1 minus theta. And you know why there is a minus? Chain rule. And you must be thinking, we did way better than this by giving it to somebody else. Why am I doing it by hand myself? Because chain rule does all of this stuff, right? So you equate that to 0. If you equate that to 0, you will get theta equal to c by c plus L, the magic solution. That means it's saying if you have seen C cherries and L limes, then the probability that you should expect a next thing to be a cherry is c by c plus L. You say, what the heck, why did I waste my time doing differentiation? That's what I would have done anyway. But now you know that calculus gives you the reason to do this. In fact, for this kind of scenario, in fact, the next one, when I come back, I'll show you a slightly more complex one, which has multiple parameters, theta, theta 1, theta 2. Basically, you have a flavor, which then also you take based on the type of flavor fraction, you put them in different kind of wrappers, probabilistically. And so you will wind up having theta, theta 1, theta 2 as the parameters. At this point, the likelihood expression will be more imposing. Theta power c, 1 minus theta power L, theta 1 power rc, 1 minus theta 1 power gc, blah, blah, blah. You put a whole entire log, it will become a nice big sum. Except now you're trying to compute the maximum for this expression, which is a 3-variable expression, not a single variable. So I take partial derivatives, equate it to 0. And again, it will tell you exactly what you would have done. And one of the most beautiful things is for Bayes networks with complete data, however complex looking the network is, in the end, maximum likelihood estimates of probabilities are the obvious ones, which is the total number in the denominator, the number with the property that you're looking for in the numerator. That's it. This is Bayesian learning. You thought, why didn't he say this? Would have been done 5 minutes after the class. But I'm just saying, I got you to tell that there's a much harder way of doing stuff. And if you approximate, you'll get here. And this is for complete data. We'll continue from here next class, the last
I just get bored. So, Saturday.